Hi folks, and welcome to Open Analysis Live. So today we're going to be doing something a little bit different. We're going to be doing a couple tips that might help you with your reverse engineering if you're using Python to help speed up or automate your analysis. So I've recently switched to Python 3 from Python 2.7. Been using 2.7 for like almost a decade now. And during the transition period, I've been having a lot of issues getting used to the new types and stuff like that in Python 3. And it kind of reminded me of when I was first learning how to integrate Python with my reverse engineering in order to speed up and automate some of my analysis. And a couple of tips that people gave me along the way that really helped out. So what I want to do is share some of those tips with you guys here today. So we'll do 5 tips to help speed up your reverse engineering with Python 3. So the first tip is about setting up your environment. Now I recently switched using Jupyter notebooks to capture all of my snippets and code snips and stuff like that when I'm writing small scripts to help with reverse engineering. I saw this actually on a live stream from GeoHot.
Yo, it's GeoHot!
And I thought it's a great idea because it allows you to both save all of your sort of one-off scripts and you may be able to reuse them later on. And also it allows you to add Markdown to keep some notes and stuff along with your code, which I find is really helpful, especially if I'm using the code to parse new binary formats and stuff like that, where I want to keep some notes about what I was doing. So Jupyter is very easy to install. It's basically just a pip install JupyterLab, and then there you go. It'll run with your regular Python environment. And what it does is it creates a notebook, a Markdown style notebook that you can save your code in, and it has a kernel which will run kind of like a live interpreter, and it has a web interface that you use to access it. And I'll show you that in a second. But before we get to that, I want to add a little flavor to it. This is what I think makes this tip actually very helpful, and that is to save your notes into a Git repository. So here on our OALabs page, we've set up a lab notes Git repository, and this is where I am keeping all of my notes from now on with snippets of Python code that I'm using for config extractors or parsing binary objects, stuff like that. Code that I don't want to lose, but isn't big enough to live as like a standalone module that I'd put into its own repository. So all those snips are now being kept in notebooks here, and you can see here I have a Python 3 one, which we're going to be talking about today, and in the reversing tips notebook is where I'll be putting in our tips for today. I also have this examples notebook where I keep a lot of Python 3 specific examples, things that I get stuck on sometimes. And you can see here, what's cool about this is these Jupyter notebooks will actually render in GitHub, so you can browse them kind of like a micro blogging service. It's really neat. It's almost like you're creating your own little blog post. But then I'll show you in a minute, you can actually download these, pull them from our GitHub repository, load them up in the JupyterLabs notebook, and run the code. So it's very cool. I've only been using this for about a month now, but it's so far I found it really helpful. And it's good if I like have a snippet of code, for example, these unhexed strings, which we'll be talking about in a minute. I like to keep these functions around just to use in my code, and it's nice to know that I have all of them stored in this one repository. Okay, so let's go through how this is actually set up, and I'll show you a little example here. Pop over to our command shell. Okay, so you can see we're in our GitHub repository here that I've cloned from GitHub, and if you do a git status, you can see it's clean, up to date, everything's pulled and ready to go. Now, the trick here is to actually launch your JupyterLabs notebook or your JupyterLabs kernel from the root directory of your Git repository. So what we can do here is just do a JupyterLab, launch it here. It's going to launch the kernel, and it'll give us this little URL here that we can then copy into our browser. And now we have our labs all set up. And the cool thing about this is you can see here in the root of our labs notebook, it's actually the root of our Git repository. So any folders that we add here will be added to our Git repository, and any notebooks that we add, for example, this one that we're working on right now, the reversing tips, anything that's saved here, we can actually push up to GitHub once we're finished. And then that way it's nice for sharing the notes, and it's a nice central repository that you can actually browse to without having to have JupyterLabs open. So that's our first tip for setting up your environment for small snippets that you might want to save for later. And also go ahead and clone our repo. If you want to add any pull requests with interesting notes that you think might be helpful, go ahead, I'll accept them. And of course, if you want to just set up your own repo and use it offline for yourself, it's still very helpful to have this nice versioned history in Git. Okay, so let's take advantage of the Markdown here. I'll add a title here, 5 tips to level up your engineering with Python 3. And our first tip, one, is to use and a Git repo. Okay. And one thing that I do want to note here, if you are going to set up your environment like this, I would recommend that you steal our, let's go in here, GitHub lab notes. I recommend that you steal our git ignore file because we've actually included a few things here that will help you ignore extraneous files that are created by running that JupyterLabs kernel. And that way you'll only be pushing up the notebooks to GitHub, and you won't have to worry about pushing up any like transient data or anything like that. So steal our git ignore if you want to set up your own Git repo, and then you should be good to go. So we'll just put a little tip in here to steal our .git file to filter out the junk file. Okay, and that moves on to tip number 2 here, which is remember the difference between binary strings and regular strings because it matters in Python 3. So I'm going to show you an example of this. This is what trips me up the most using Python 3. Those of you who just start using Python at Python 3, you probably won't have much trouble with this. For those of us who've been using Python 2.7 for a long time, it's helpful just to have this tip, and I'll copy over a couple examples just to show you what I'm talking about. So remember, binary strings are not strings. And we can shift enter, and it turns it into Markdown. Now we have a new interpreter, which is set to code in Python. And what I'll do is I will copy over an example from our example document here, showing the difference between a binary string and a regular string. So, or a byte string. Ooh, I've been saying binary the whole time.
I'm going to be honest with you. I'm kind of retarded.
Should change that to byte. Okay, so here's what I'm talking about. So in old Python 2.7, you didn't really have to worry about this too much because there was a behind the scenes conversion type thing going on, and the strings would default to strings, not to byte strings. However, now these types really matter in Python 3, and we end up with a lot of incompatibility issues where you'll think that you're working with strings, and in fact you're using byte strings, and you'll get a bunch of errors. So the best way I found to deal with this is to just prepend that B in front of all your strings, only work in byte strings, because of course this is for reverse engineering, so we're going to be working with binary data most of the time. So it's just easier to just work in byte strings. That's the way that I like to work now to avoid any confusion. However, if you are switching between strings and byte strings, you will want to remember, and this is what gets me every time, if you want to go from a string into bytes, you encode, and when you want to go from a byte string into a string, you decode. To me, for some reason, it seems like it should be the opposite. I don't know why, but I always flip these around. And also remember that UTF-8 is the same as ASCII, so this is a single byte is a single letter. UTF-8 encoding, that's probably what you're going to be using most of the time for ASCII strings. So just to show you guys the example here, so you can see the difference here. If you print out your encoded a string that's being encoded into a byte string, you have that little B before it, and if you're going from byte string to string, you lose the B, and it's actually being interpreted as a string now. Again, I won't go into too much detail. I have this other examples note that has all kinds of different examples showing you how to go through and test different formats of this. If you ever get stuck, you can use it as a reference. I certainly do all the time. But this is just here as a reminder that you do have to keep those separate. And again, my tip is if you're working with binary data, if you're using Python to interpret binary data and parse it out and stuff like that, you're writing a lot of config extractors, stuff like that, just use byte strings and you shouldn't have any issues. Okay, so before we go any further, the last 3 tips are going to use an example to demonstrate what's going on. I find it's a lot easier if we just have a simple contrived example to show you the power of these tips rather than just having some sample code here. So what I'm going to do is I'm going to set up our example. So I'll do an example, tips 2, 3, 2, 5. Okay, and so we're going to do example data. And what I've done is I've created, remember that binary string, I've created this contrived example where we have a bunch of binary data. And so I'm just going to copy it out as a binary string here. And we're going to use this to show all of our examples for the next 3 tips. So I've just saved it here, and then we'll move on to tip number 3, which is talking about hex encoding strings for easier copying of binary data. So tip number 3. Okay, so what am I talking about here? So in some of our past videos, you probably see me copy data out of IDA using a script called hexcopy, or a plugin called hexcopy that I developed. And basically what this allows you to do is copy binary data as a string and not have to worry about escape characters and stuff like that. So it actually copies the data as a hex encoded string. And this functionality you'll find in most of your reverse engineering tools. So like x64 debug also has a copy as hex encoded strings feature in it. So this is how I mainly copy binary data between programs, because you don't have to worry about escape characters. You don't have to worry about it messing up your clipboard, because everything is just encoded in hex encoding. So when it comes to Python, what we need is a quick way to decode that hex encoded string into the binary data so we can actually manipulate it as binary data. and then a way to encode the binary data back into a hex string so we can copy it back into our reverse engineering tools. So that's the main reason why I'm using hex encoding, is so that I can copy binary data between my different tools. Now in Python 2.7, this is very simple. You would just do something like, here's your string, binary string, and you would do encode as hex or decode as hex, like that, basically, right? But that doesn't work in Python 3, and very frustratingly, there's a bunch of different ways to do this, but I find the easiest way is to just use the bin ASCII library. And I have an example of this as well here. So I'll actually copy it out just so it's all in the same note here. So what I've done is I've created these two functions, which I basically copy into all my scripts now, unhex and tohex, which import the bin ASCII library, and then they use the bin ASCII unhexify and hexify to convert between hex encoded data and binary data. So we can just use these with our example data here, and I'll just show you what the hex encoded data looks like. For those of you who aren't familiar, I'm sure most of you have already seen this before, so I'll go through it nice and quick. The other thing that I've done is I've also added this encode from UTF-8, so ASCII encode. In case the function is passed a string instead of a byte string, I'll just automatically turn it into a byte string. So it's just a little helpful extra thing, so I don't have to worry too much about what I'm passing to the function. And like I said, I basically just copy these functions everywhere, so I don't have to think about it. So what we can do here is we can do a print. This is hex encoded data, and we'll do 2hex of our. All right, so this is what it looks like. This is your hex encoded data. And where you've probably seen this the most is if you do a hex dump of a file, this is the same format that you'll see. So I have a copy of this example data in a file called example.bin in my temp directory. So if we cd into the temp here, and we can do a hex dump c of example, there you go. So it's the same encoding here. These hex bytes are the bytes of the file. And of course we show the ASCII bytes here in hex dump. And that is what we have in our Python script here, right? So again, this is just an easy way to go from hex encoded strings, which you're using to copy data between your tools, and then converting it into binary data so you can actually work on the data. So that brings us to tip number 4, which is talking about the library struct. So we'll do markdown. Tip number 4, use struct to convert data and types. And actually, I'll just add a reference to the struct library in here. So what am I talking about with struct? Well, let's do Python struct. Okay, so this is the struct library. It's standard in Python. And what it allows you to do is it allows you to convert between, there's an example here. It allows you to convert between the binary format of a type and the actual type. And it supports all of these different types. So basically all your standard basic data types that you'd be using when you're reverse engineering binaries. You have everything from a single character to a D word, which in this case is like an unsigned int, capital I, that's what I use most of the time. It supports endianness, so you have a little endian by using this less than sign, greater than sign is big endian. There's also other formats here, network, which is actually just big endian, but you know, if you didn't know that, you could use this network indicator format. And of course, you can go both ways. So you can either pack into data or you can unpack, which is converting from binary data into the type. So I'm going to show you guys some examples of this now, and I'll use our example data here. So before we get into this, we need to talk a little bit about what this example data contains. And what I'm going to do here is I'll actually just create a little markdown section, and I'll copy it up here and explain what this is. So our example data is a structure that we're going to have to parse. And the structure is composed of a D word that tells you how many strings it contains. And then each string has its own structure, which is composed of a Boolean that tells you whether it's a wide string or an ASCII string. So if it's true, it's a wide string. If it's false, it's an ASCII string. Then it has a D word that gives you the string length and then the actual string. So let's just add a note here that explains that. So our example data structure, and we'll make this 3. So we could do something like this: struct strings, and the first thing is a D word, and that is the number of strings. And then after that, you have an array with your strings in it, and each one of the strings is composed of a Boolean. So it's your your string boolean that says is wide string. You have a string length, which is a D word, and then you have the string itself. Actually, let's go back and make this proper format. Okay, so this is our format. So now to illustrate how the struct library works, what we can do here is we can parse out this example data, and let's say we'll just get the length of strings. So let's use the struct library to tell us how many strings are in this stream. So we'll do number of strings equals struct.unpack, because we're going from binary type, and we're going to do a little endian unsigned integer. So little endian less than sign, unsigned integer, capital I. And you've probably seen me do this in some of the other videos that we've done here. So unsigned integer, capital I, and then we want to parse out the example data, and we're going to grab the first 4 bytes of the example data, and then we're going to grab the first type. Now the reason why I have to add on this little array indicator on the end of our struct unpack is because the unpack command will unpack as many of those types as it can find in the data. So we only have one type of D word because we're only grabbing the first 4 bytes. So we just want to grab the first one. And of course, that's the number of strings. So once we grab that, oops, I jumped the gun here. Let's import struct, and let's print this out here. Print the strings, and it's an integer strings. Okay, number of strings is 2. And of course, that makes sense because if we look at the first 4 bytes here, that is 2 in little endian format. So here you can see the power of the struct library. We are now working with a number that we've parsed out of our binary data. We've made some sense of that binary, and it's all thanks to the power of the struct. And of course, you can do that for any of these types here. So we have a bool, a D word, a string. I'll show you how to do the strings. You don't need to use struct for that because you can actually just convert that using this, of course, right? You can convert from a byte string into a regular string. So I think that brings us to our final tip here, which is to use what I call a custom structure or custom struct. I'm not sure what the term is for this. I certainly didn't invent this. This is something that I picked up along from some of my colleagues. But basically what you can do is you can create your own Python structure using a class, and then you can use that structure to automatically parse out binary data like this, and to capture the structure of that binary data so that not only can you parse it, but you can also write or overwrite some of the fields in the binary data. Now on its own, this is just kind of a cool thing with an interesting example that we have here, but in practice, you'll find if you look at some of my code on my GitHub or config extractors, you'll see that I use this all the time. When I have a config file for malware and I'm parsing it out into its different components, I'll use this sort of custom struct idea that I'm going to show you guys here. So let's get in some markdown here and we'll just explain this tip. So it's tip number 5, and this is use custom struct class to parse binary data. Oops, forgot our, there we go. Okay, so in order to do this, we're going to break this down into 2 parts to make it a little bit less complex. And in order to do that, we're going to grab this first string here. It starts after 1, 2, 3, 4 bytes. We'll grab this first string here, and we'll use this as an example string because, of course, this is a list of strings with another structure on top. And I want to show you the power of using nested custom classes. So we'll start easy with this example string, and then we'll move up to parsing the example data here. So to parse this out, we know that the structure is a boolean that tells us whether it's a wide string or not, a D word that tells us the length, and then some length of characters of a string, which is determined by this D word. So the first thing we want to do is we want to create our class here, and we need to call it something. I think I'm going to call it example string. Of course, that's arbitrary. It doesn't really matter what it is. And we'll need our init class, of course. And now in our init, what we're going to do is we're going to create an empty structure that looks just like this. So we'll do a self dot is wide string equals false. We'll do a self dot length, string length, and that is going to equal x0. And we have a self dot string, which is empty. Okay. Then what we want to do is we want to add 2 functions that are going to help you pack and unpack your struct. So let's do def from buffer copy. And you guys might notice that this looks a lot like the C types structs. So we're not going to get into that. I find this is actually easier to work with. It's a lot more customizable. But those of you who have worked with C types, which is a Python library, library before, you'll recognize this. So from buffer copy, basically what we want to do is we want to copy and populate this struct here. Now, we know some of the length of the struct, but not all of it. So we're going to have to go piece by piece. And this is the power of parsing binary data with structs like this, is you can parse a stream of data without having to know the full structure beforehand. Now, without getting too much into detail, this is things like the proto buffers and stuff like that, which you might have seen in some malware. This is like basically the same idea, only it's completely extensible. So you can use it for any sort of binary data parsing that you need. There's no limitation to it. So the way that this works here is I like to just do a pointer and I'll initialize it at the beginning of the data stream. Then I grab piece by piece to fill in the struct. So the first thing we know is we know that the isWideString is in fact a Boolean. So we know that's going to be a single byte, and we can use the struct library to pull that out right away. So let's actually import struct here. We've already imported it above, but it doesn't hurt to import it here as well. So starting at the beginning of our data buffer, we're going to copy out the isWideString Boolean. So we'll do self isWideString Boolean equals struct.unpack, and we have to look up the character for Boolean, which I think is a question mark. It's a question mark. And since it's a single byte, we don't need endianness. We'll do single question mark. And that is the data. This is the first byte of the data. Actually, we'll do it this way. Pointer plus 1. That way it'll be consistent across all of the copies here. So we pop that out and remember to grab the first type that comes out of that struct unpack. And then what we can do is we can increment our pointer equal 1. Okay, so now we're on to the length, which we know is a D word. And so we can do self string length equals, and of course we already have this code here because the length is the same for both. So we'll do data at pointer plus 4 bytes in a D word, and we'll grab the first type. And again, we remember to increment our pointer. Okay, so now we know the length of the string, so we can actually use that to then copy out the string. So we'll do self string equals data from the pointer to the pointer plus self.string length. Okay, now you guys might be saying, hold on a minute, this isn't right. What if the string is wide string? So wide string is 2 bytes per character instead of 1 byte. So the length of the string doesn't change, but the length of the binary data doubles in size. So we actually have to account for this by adding an if statement here and do if is wide string, then we need to do something there, else this will work. So if it's a wide string, we need to do something else. So wide string, we need to copy twice as many bytes, and we need to decode. No, see, I messed up. That's why we have our helper here. So if we want to go byte string into a regular string, what do we need to do? Convert bytes into string, we need to decode. So we need to actually decode it. And of course, it's not going to be UTF-8, it's going to be UTF-16 because it is 2 bytes. So with Python, when you're decoding and encoding wide strings, there's one extra thing you need to keep in mind. By default, Python will prepend a byte order mark, so a bomb, to the string that it's encoding or decoding. Now, this is good if you're writing out like a text file that needs to be opened in like a text editor, which the encoding mark actually matters. But for us, when we're converting between binary data and strings, we don't want that bomb. That's actually added data that's not necessary. And of course, it could mess up our configurations and stuff like that if there's no bomb included in the configuration file that we're working with. And in our configuration file, there is no bomb. In most malware, they don't have that. It'll just be a wide string or it'll be an ASCII string. So in order to tell Python not to prepend that bomb mark, we need to just add a little LE here, which means little endian. And this encoding, even though it's a little weird to add that LE, will actually give us back the data that we need. And we need to remember this when we're writing data as well. So now the last thing to do is to change our pointer. So we need to make sure we increase our pointer plus equals string length times 2. And in this case, pointer is going to be incremented by the string length. Okay, so now we have a way to parse out this string and all of its data from the binary data here. What we want to do now is we want to create our second helper function, which allows us to write this string. And this is actually a little bit easier because we don't have to make any calculations. We're just going directly from the struct definitions here to a binary string. So we'll do def pack or self because it's class. And we want to do data equals, we'll start with an empty string. We'll do data plus equals the struct dot pack, and we can use, we know that the first thing is this boolean, and we can copy it from our internal data here. We want to do data, scroll up so we can see it, plus equals the length. So we'll do a struct.pack, the little endian, and this will be string length. Then if the string is ASCII, so we have to do a little test here again. So the string is wide, actually, we'll come back to that in a minute. So if it's ASCII, it's very easy. We just do data plus equals self.string. And we'll, of course, we forgot our decode here, which, like I said, I always forget this. Decode. And UTF-8 doesn't suffer from the byte order mark because there is no byte order because it's only a single byte, so you don't have to worry about it. So we're going to have to go from string to encode UTF-8. And of course, if it's a wide string, we're going to have to do the same thing, only we're going to encode it using UTF-16 little endian. All right, so now we have our example string structure, and I'll show you the power of this, all of that work for this simple example here, where we will do print data, example string data, and we'll just print out the raw data first. So we have it on the screen here, print it as raw, and we'll grab the example string here. Okay, right? What we want to print now is we'll print out we'll parse it. So actually that's the first thing we should do is parse it. So we'll do our ES equals instantiate our class here. Then we'll do ES dot from buffer copy, and we'll copy in the example string. Then what we want to do is print all of the different fields out and make sure that we got this right. So let's print out example is wide, and this is Boolean, of course. So we'll do ES dot is wide string. Then we'll, oops, there's a string here. So that looks like that's working. And we'll actually probably just copy this and make it a little bit faster here. So example string length, and this is the string length. Of course, we want to print it as an integer, and then we want to print the example string, and we'll print that as a string. Okay, so there we go. We've actually parsed out the all the different fields from this binary data, and we have it sitting in a string here. And of course, we could alter it if we wanted to. So we could do something like, let's say, turn it into a wide string. So es dot is wide, it's true. Okay, and then we'll pack this data and we'll print it out as binary data and see what it looks like. So convert it to wide, and we'll do es.pack. Okay.
All right. What?
Oh, and of course, I've already forgot our second tip here, which is to remember byte strings are not strings. And so this is actually probably a good example just to show you guys why that errored out. We need to make these byte strings and empty strings. So like I said, I still get caught up with these, especially with the empty strings. I forget to convert them into byte strings, but this should work now. We should be able to pack this.
What?
Yeesh. Oh, and of course, I forgot to return data. Lots of errors here. There we go. So now you can see we can actually write to this binary data after all those mistakes. So we can convert it from ASCII string into wide string and then maintain the structure here. And of course, the string length is still 4, but it's wide bytes, so it's going to be doubled in size. And you can see the TEST all split up by null bytes here. So hopefully that's a good example showing you how to create these custom structures to parse stream data or parse binary data and not having to worry about a predefined structure. You can basically parse it as you go, and you can see once you have the structure defined in your code, it's very easy to convert between, change values, convert between binary and types that you can work with. Now to finish it off, tip 5.1 or whatever, what we'll do is we'll actually parse out this full stream here. So we've just created a class for this right here. What we need to do is create a class for our full stream of example data here. And what we'll be doing is we'll be reusing this example string in our class. All right, so we should be good to go here. And so let's give this a try. We'll do es equals example strings, and then we'll do an es dot from buffer copy of our string data here, right here. All right, let's run this, make sure it works. Works okay. So now what we can do is we can do stuff like how many strings are there? So print the number of strings, %d, and %es.length. So there's 2 strings in there. Let's print the first string. First string, strings 0 dot, and I think we call it string, right? First string is test. Let's print the second string. Oh, second string is test as well. What's the difference? Well, as we can see in our data here, first one is ASCII, second one is a wide string. And we can just confirm that by adding that data in here. So let's print, first string is wide, and we'll do is wide string. And we'll do the same for the second string. All right, first string is wide, false, test. Second string is wide, true, test. So hopefully now you can see the power of using these custom structs to parse your binary data. It does take a little time just to set up the helper functions and stuff like that. But if you're doing a lot of parsing of binary data, I highly recommend doing it this way. And you can see the flexibility in not needing to know a defined structure beforehand. You can actually parse as you go, which allows you to parse data streams. Of course, this is one of the more difficult tasks to do when you're parsing binary data, is to parse a stream which has an unknown length, right? Which you determine as you go. This is one of the more difficult things to do. And using these custom struct classes will take care of all that for you. So there you go. 5 tips to help you level up your reverse engineering with Python. I hope you enjoyed this. I will push this notebook to our GitHub, so you'll always have these code examples. And if you have your own tips, stuff that you think I missed, let me know in the comments below, or do a pull request for our notebook here, and I'll try and add any pull requests I can to our Git repo here so that we have a nice repository of Python 3 tips. And with that, until next time, keep exposing the mechanics behind the malware. Stay curious.
You know you fucking feel me. Yeah, you know you fucking feel me. Yeah, you know you fucking feel me, right?